Okay, everyone, welcome to my talk about OpenMP. We're going to cover OpenMP, and along the way, I want to talk about a big point I push, which is there's actually a small number of design patterns we use over and over and over again in parallel programming across languages. And the difference between an expert parallel programmer and a novice parallel programmer is the expert knows those design patterns and knows how to express them in different languages. So it's the patterns that matter. And then it's just a little detail to how you map them into OpenMP or MPI or SYCL or COCOS or whatever. So in terms of getting from novice to true master, the sooner you get to thinking in terms of these reusable design patterns, the better. So we'll get there. Okay, so, how do I advance this? There we go. All right. So introduction, thank you for introducing me. As I like to say, my real passion in life is a kayak instructor. That's on Pacific Coast, about a 5-minute walk from my house. Life is good. And I like to say that I support my kayaking habit by making lines on speed up plots. So that's what I do. I get paid to make lines on speed up plots. So it's pretty cool. I do, though, work for a corporation. So I always have to put this up, which basically says, don't sue me, which says you may not possibly be able to reproduce any numbers I show you whatsoever. And please don't sue me. This is so important, I want to be really clear that the views in this tutorial are my own. I'm not speaking for Intel. So I've not had an Intel lawyer check these slides. And also, I take these tutorials very, very seriously. So, if there's something you think didn't work or something you thought worked particularly well, take a note and send it to me at some point. My email address is real easy to find. So there we go. Now, if you've never taken one of my tutorials, I do things differently. And frankly, they work very well. I'm a professionally certified kayak trainer, educator. I train people to be kayak coaches. And I've learned how to teach through that. So I teach you OpenMP the way I would teach someone how to kayak, how I teach someone to do athletics, which is you don't learn from words, you learn from doing. So I give lectures to lay out the concepts, but the real learning happens with exercises. And so we will spend at least half, if not more, of our time together, you doing exercises. The idea of you listen to me lecture all morning and then do a few exercises, that doesn't work. I lecture for 15, maybe 30 minutes at the tops, and then you're doing something. You can do all of the exercises on a multiprocessor laptop if you have an OpenMP enabled compiler, or you can use the systems that are made available to you through this course. Your choice. It works just fine everywhere. But I want to emphasize, don't cheat. If you pull down the exercises, there is a solution folders. So, you can just cheat and go straight to the solutions. And if you do that, you won't learn anything, because some of the exercises are designed to frustrate you, because adult human beings learn by pushing through frustration. So there are times where it's like, you didn't tell me enough to do this yet. And it's like, yeah, that's the idea. It's called guided discovery. I set up a problem. It's how coaches in athletics teach. I give you a problem to solve, and you're going to learn something solving the problem. So don't cheat. Now, if you already know a bunch about OpenMP, don't get bored. So what you do is then do the exercise as I gave it, and then play. What happens if I try 1,000 threads? What if I run my loops in reverse? There's just play and explore. So that's the ground rules for today. Now, normally I have to spend a really long time on the systems for the exercises and all of that. But I don't think I need to, because you you did the MPI sessions yesterday, and in the MPI sessions, you got on to systems and you used the different systems out there. If you go to the GitHub or you go to the resources, you can link through the program page. You can get a copy of these slides, and you might want to make sure you have a copy. So if you get stuck, you can go back to the slide and get all the details for how to run. But you know, the idea is you need to have the compiler, you need to either get an interactive node or submit to the batch queue. I'm assuming you all know that, but when we get to the first exercise, I've requested that the knowledgeable people of the systems you have available to you will be around so we can talk and work through them. So I'm just going to skip through these, but you know, you have them to refer back to. So that's that. Let's start with OpenMP. Now, I just want to point out, I have on my other screen that you can't see the Slack session. So if you have immediate questions, don't be shy about plopping them into the Slack session. I will see them real time. And if there's something of interest to the whole group, I will respond in real time to the whole group. So here's our agenda for today. Pretty straightforward. We'll introduce OpenMP, create threads, synchronization, and we'll work right on through. And sometimes, depending on the group, it takes the whole day just to get through to that session recap. And so I really have to wait and see, because since this is driven by exercises, it depends on how fast you get through the exercises. If we have time, we will then go into that beyond the Common Core section and cover some of these other topics. So there we go. What is OpenMP? So OpenMP is an API for writing multi-threaded applications. When we started, the goal was to make the simplest system we could for writing multi-threaded code. So this was as easy as we knew how to make it, was the idea. Most everything that happens is through a compiler directive. So OpenMP is bound to a compiler. And so we have a few runtime library routines for things that can't be done at compile time. But a lot of it is you give the compiler a directive, and that tells the compiler how to generate the code so that things will run multi-threaded. And the idea, as if we said earlier, is to make as simple as we could make it for Fortran, C, and C++ programmers. And we did it right, which is, and the reason we did it right is we had the MPI process to learn. Historically, MPI happened in the earlier part of the 90s, and OpenMP happened in the latter part. And most of us working on OpenMP also worked on MPI. So, you know, we had the success of MPI to guide us. And one of the key things of MPI and one of the key things of OpenMP is we didn't do anything new in the original standards. The idea was standardize what we've been doing, so we're sure to get it right. Now, over time, I love showing this slide to my friends in the OpenMP community to tease them. I was actively involved as my full-time day job up through OpenMP 3.1. Gee, and I stepped out and look what happened. This plots the number of pages versus the year. And you know, you can see that when we started, we were around 40 pages, and now we got up to close to over 500, well, around 500 pages. Fortunately, the latest version, which is should be coming out this November, has come down in the page count. But the thing is, everything was about simplicity when we started. Everything was, we got to make this easy. And right now, if you think about the whole spec, it's become this complex thing just for experts. And that's not good. And so what I have found, though, is if you talk to OpenMP programmers and you look at OpenMP code, even though this spec has become this thick, complex book, most people only use these 21 constructs. They only ever use these 21 constructs. So the way to learn and think about OpenMP is there's this simple, I call it the common core, this very, very simple core part of OpenMP. You master that, you learn it deeply and use it and master it. And only when you hit something that you can't do with the Common Core, you look it up and then, you know, dive back into the spec or some of the books about OpenMP and go there. And if you do that, then it stops being this scary monstrosity. And frankly, this is also how you work with MPI too, because if you just look at the MPI and start reading the spec, you'll run away screaming. But you come back and you realize what there's really only 10 or 20 things we use all the time. So what we're going to do today is we're going to cover the Common Core so that you'll walk out of here ready to do hardcore professional programming in OpenMP. So let's get some basic definitions out of the way. At the bottom is the hardware. And today with modern OpenMP, we cover the bases. We cover, it's multi-threading, and anytime I say multi-threading, I'm assuming a shared address space. That's what the word multi-threading means. So there's a shared address space, and OpenMP even has the ability to manage the non-uniform memory architecture features of a modern architecture. We also cover GPUs, so we have incredible hardware diversity. On top of that is what I call the system layer, and I like to emphasize this, that when we talk about threads, we are using the threads the system gives us. So I have some people sometimes ask me, well, I have this great program in P threads, will it run faster with OpenMP? And I'm like, probably not, because OpenMP just maps down into the P threads if you're on a system where that's the native threading layer. So we run on whatever the system gives us as the lower layer threads. Then there's the programming layer, you know, the directives, the runtime library, the environment variables. And then on top of that, I have the user layer, which is the applications that end users run. So these are the basic layers we're talking about when working with OpenMP. And the topic of this tutorial is that programming layer. We will, by the end of today, if you stick with me, you will have mastered that entire blue programming layer. That's what we will cover. Now, there's one more thing. Most of today, we're going to only worry about this model of the hardware, the shared address space, SMP, and being an old guy, I'm a stickler for using words correctly. And so this SMP means symmetric multiprocessor. It gets abused and used in different ways. So let me tell you, the term symmetric multiprocessor means you have a bunch of threads and they're all the same as far as the operating system is concerned. And they all have a equal cost function to different locations in memory. That's the crux of the matter with an SMP model. And so we're going to focus on that. Even though we know that most machines don't quite meet that model because of caches and other stuff. But this is kind of the opening approximation. And most people working with OpenMP, they assume this SMP model and expect the system to kind of flesh things out for them. And it does a good job in most cases. All right, so one more basic, boring background slide before we dive in. Now, we were very, very careful to design OpenMP so that you learn it for one language and you can use it in all the languages. So it works in C, it works in C++, and it works in Fortran. Now, this tutorial, I'm only going to cover C because I don't care what language you ultimately use. If you're an HPC programmer, you need to be familiar and comfortable working with C. So, but we only use the most basic of aspects of C. So don't worry if you're not an advanced C programmer. You don't need to be an advanced C programmer. So we're going to work with C. And even if you're a Fortran programmer, we're going to be using just the very basics of C. So it won't be a problem. You won't have a problem. Okay, so in C and C++, your compiler directive is in the form of a pragma. So it'll always be pound, pragma, OMP, the construct name, then a set of clauses. If you're in Fortran, you're going to have some sentinel for a comment. If you like C, you can use C. I guess modern programmers use the exclamation point. But exclamation point $OMP says that this comment is an OpenMP directive, then the construct name and the clauses. And the big thing is the construct names are the same between C and Fortran, C, C++, and Fortran. The only difference is that in C and C++, it's a block structured language. So within the core language, I can have my open bracket, close bracket. So with Fortran, though, it's not block structured. So with Fortran, we have to add this end version. So don't worry, we'll talk about what these constructs mean. But with Fortran, I'd have the exclamation point $OMP parallel, and I have to pair that with a close to the block. Exclamation point $sign OMP end parallel. Okay, that's the only difference. Well, there's one other difference we'll get to maybe much later, but really that's the only difference. You learn this for C, you know it for Fortran, and that's really cool. So here comes the first exercise, and this is in some ways the most difficult exercise the whole day. Maybe not, because you folks had yesterday to work with the systems. Whatever system you're going to use for the tutorial, I want you to get onto that system, open up an editor, write a hello world program, and then compile it. All right, so this is where we get through the issues of compile it and run it. Okay, whatever system you're going to use, and if you have problems, get help. But I'm assuming this part is trivial, so go for it. Now, I need a way to see when you are done. Okay, while you are doing that, I'm going to be changing. I need to share my screen because I need to see the rest of Zoom. I'm not getting the other Zoom elements.
Tim, when you're in screen share at the top bar, you can bring down the chat, or I'm not sure what else you're trying to see.
Well, normally, yeah, I was going to ask people to raise their hands or somehow give me some indication when they're done.
Sorry, I muted myself again. I think you can still bring down the participant list while you're sharing. You need to go to that bar where the end share is, and one of the buttons on it has other options or something like that. And you can pull that down.
Sheesh. Okay, that's back. I'm no longer sharing. I really want to share my screen because sometimes I need to pop up code.
Okay.
And so while everyone's getting their...
yeah, one of those tiles is for the full screen. It's usually at the beginning. Okay, yeah.
Click that. Gosh, it's so weird that my PowerPoint is acting differently than it normally does. But this works, right? Everyone can still see that just fine, right?
Yes. We can see your whole desktop.
That's what I want, because see, then I can pop over here and say, oh, well, I can do this exercise too. You know? Okay, so we got that. You were screen sharing. I guess we're communicating, you are communicating to me through Slack. But aren't there ways for people like to raise a hand or to float some emoji or chat? why don't we have when you're done? Ah, okay, good. I got a chat window. We're gonna figure this out, you know? When you're done, just put something in the chat window of Zoom that, yeah, done. There we go. Cool. All right, so you got on a system and you compiled this. The next thing to do is the second part. Okay, looks like everyone's done. This is cool. Okay, so the next part is, and I'll explain all this later, but just go in and at the top of your file, put pound include omp.h, and then put pound pragma omp parallel, open bracket, and then after the printf hello, printf world, put the close bracket. So now compile it. Now compile it, putting the switch on the compiler, telling it to include OpenMP. And that's usually if you're using a GNU compiler, that's a -f OpenMP. On Theta with your compiler driver CC, it's -q OpenMP. But what I want you to do is on whatever system you're using, put in the switch for OpenMP, compile this and run it, and see what you get. So this is an important exercise because this is where we see that, you know, do you indeed know how to access your OpenMP compiler? So for me, that wasn't what I expected. Oh, of course not. I didn't add the OpenMP constructs. You know, it's always scary doing anything live that involves code in a tutorial. All right, now let's see what happened. And if you're having trouble, let us know in that Slack channel, because, you know, as I said, this is the time to get system access issues. Yeah, GCC 9. So I'm running on an Apple laptop, and Apple has done something profoundly irritating, is they map GCC onto their own Clang-based compiler. So it's an alias on my own laptop that GCC-9 goes to the an actual GNU compiler. So I couldn't believe that Apple did that. Oh, I know. Apple has no respect for standards. That's one of the reasons I'm going to leave Apple. I can't believe I'm going to say this, but I'm going to return to Windows. because they have so little respect for standards. It's beyond irritating. They need to be punished. So
they believe in standards, the one they set.
Yeah, that's right. They set something and call it a standard. Yeah, that's just irritating. So
until they change their mind.
Yep. So I'm, at the corporate world, they like either Apple or they like Windows. I have to choose one or the other, so I can't. Linux is not an option. And I left Windows 10 years ago, because I can pretend an Apple system's Linux, but they've just gone too far. So, and I haven't used it yet personally, but I hear the Linux session that comes with Windows 10 works pretty well. So if you are having problems, it's important for you to let us know. Because from this point forward, I'm going to assume that you know how to edit a file on your system of choice, to compile it with OpenMP, and to run an OpenMP program. I mean, that's the learning goal we have right here. So if you are having problems, say so in the Zoom chat right now, because you're going to fall painfully behind. Yeah, that's a good question. Someone's asking how long is the average wait time on Cooley nodes when you're submitting to the queue. So if you use your own computer, the GitHub location is on the title page of this slide set, but it's also, let me slide this window in here. If you look at the program here on for this lecture today, class materials, that link takes you straight to the GitHub page. So just clone this repository right here, and you will have everything. You'll have the PDF of the slides, but you'll have all the exercises right there. So I know for me personally, I advise people to do this on their own laptops, because then when you walk away from this, you still have an OpenMP system running on your laptop and everything's fine. The problem is that it used to be OpenMP was well supported by default everywhere. But now, like if you're on an Apple system, you need to download a GNU compiler, and Windows, actually Visual Studio has OpenMP, but like at version 1.5, it's so old, it's unbelievable. So at any rate, okay, I'm going to move on. Do I have a sample submission file for Cooley? I wanted to put it on this page, but so here's what you do, is you put this command right here in a JavaScript file, and then you submit with this QSub.
Tim, that is about the data. And I think if you want to use Cooley, you can use the interactive mode on the Cooley, right? So in this page, the QSub -n, -1, -t, and 60 minutes, and the Q should be training, and otherwise it'll be same.
So you're saying this here should be training, not ATP?
Right.
Now, my concern with that is, do we have enough nodes if every single person here were to try and grab an interactive node?
I think so. So in this page,
I believe there are 80 nodes on Cooley just waiting for you to use them.
Wow. Okay, so you can grab.
As long as somebody doesn't ask for 79 of them, we're good.
Well, and remember, everything we're doing today is on a single node. I'm not going to try and cover MPI today. I'm not going to cover MPI and OpenMP combined because I think it's good to just really master OpenMP. So you only need one node. Okay. And for those of you experts on those local systems, so you grab an interactive node, build and run your program, and then you run it with this line right here, right?
On the Coolie, you need to use MPI run. So this is kind of
MPI
confusing.
run, even though we're running OpenMP?
Yeah. Okay, on the Coolie, you don't need to use MPI runs. You can just use AWT, right, as you did. So this page is about the data. So it's kind of confusing.
Oh,
the
gosh.
Coolie,
okay. This is the thing.
This is getting just a little complicated, but let me try to explain. On Coolie, if you run the interactive job, I'm pretty sure it drops you on the first node of the set. So if you only ask for one node, then you're on that node and you can just run. Right?
Oh, good.
But on Theta, when you do the interactive job, you're getting a prompt on the mom node. It's not on a compute node. So you need to, even if you're running a one compute node job, you need to launch it with app run app run.
All right. So on Coolie, get an interactive node. There are enough nodes, and then you can just type a.out and everything works. Got it.
Yeah, just check where you are with a hostname command and make sure you're not confused. If it says like CC 101 or some number, then that's one of the compute nodes. I think CC is Coolie compute or something like that.
Okay. So let us know in the chat right now, the Zoom chat, if you're still not able to run an OpenMP program on your system of choice. And there was a question about what's the max wall time for an interactive job. I don't know.
I think that there is no maximum, which from a practical standpoint means if 6 p.m. minus now, that's the maximum job time.
Okay. Just as a point of reference.
Because if you put a job time that can't start and complete before 6 p.m., then it won't start the job.
Okay. Anyway, for the exercise today, they all take seconds, not even minutes. They take seconds. So nothing should take very long. Okay, well, no one said that they're hung and waited up, so that's good. So I'm gonna go back and get back to the content here. Wow, we got through the most difficult exercise. Congratulations, team. So when I ran this, I got hello, hello, world, hello, world, hello, world, world. Okay, and if I ran it again, I get it different. Hello, world, hello, hello, world, hello, world, world. And likewise, oh, no, there I got hello, worlds. What's going on? And this is a vitally, vitally important concept. And that is when you are running a multi-threaded program, the operating system is scheduling the threads. It's interleaving, giving a quantum of execution to each thread. And it's bouncing, it may run this thread, then that thread, then this thread, then that thread. You have no control over how it bounces and schedules a quantum of execution between the threads. The end result, and remember, there's lots of other threads running on the system, not just yours that you're submitting for this job. So when you run a multi-threaded program, every possible allowed interleaving can occur. That point is very important. You have to write code where every which way the operating system can interleave the statements still gives you a correct code. I call that the multi-threaded reading of a program. And I'll tell you, sometimes, obviously for this hello world, it's easy. It's like, oh, the world could be below 4. The world from thread 1 could happen before the hello from thread 0. And, you know, so it's easy in this case. But I'm sure you can imagine if I have thousands of lines of code spread out between many, many different files, it can be challenging. So I just like to warn everyone up front, multi-threading is deceptively simple, but it can be deceptively complicated by these small interleaving effects. That's why people often say MPI is much more difficult than OpenMP. And it's like, well, some ways it is, but in other ways, you don't have this issue so much with MPI. So at any rate, important to keep in mind, it's going to interleave the statements any way the program semantics allows. And we have a couple people still waiting on interactive shells. I was afraid of that. And I assume that means you haven't been able to complete the exercise. Okay, so I'm going to assume, Ray, that you can help them get unstuck, because I kind of have
I think that those are, I see 1, 2, 3, 4. I see 5 jobs submitted to the default queue, which there probably aren't enough nodes to run. The reservations, the training queue. Okay, so if you submit to the training queue, it should run right away.
Okay, so they should kill their request, or just submit the request again, but do it to the training.
Yeah, if you want, in another, you could either Control-C it and just change the queue name and do it again, or that's the easiest thing.
All right, so Control-C that and then resubmit it to the training queue, and then you should be all set. Good, I have to keep going. So I'm assuming you folks are gonna catch up soon, and don't worry, the next exercise is a long one, so you'll have time to catch up then. Okay, so OpenMP is all about multi-threading. And now you know what multi-threading is. We create a bunch of threads, and the operating system schedules them in and out of an execution context. And I can run them at the same time. And multi-threading was designed to create the impression that all of these threads are active at the same time and making progress at the same time. And if I combine that concurrency with multiple execution units, I can actually have them run in parallel and things go faster. So the fundamental conceptual model behind OpenMP, the fundamental design pattern at play for any of the multi-threading environments is fork join parallelism. So you start up the program and you have an initial thread. The initial thread gets to a point where it could use some additional threads for whatever reason. So what it's going to do is it's going to spawn a team of threads. Old-fashioned word for that, it's going to fork a team of threads. Now those threads will run in parallel on parallel resources. The initial thread is part of the team. That's why that red line continues up into the team of threads. And then when they're done, they're going to wrap things up, logically shut down the extra threads, and the initial thread will continue past that point. So when you create the threads, that's called a fork. When the threads are done, it's called a join. And then that initial thread keeps cooking along through the program, and it hits another point where it needs additional threads. Fork a team, do your work, join. So your program becomes a sequence of parallel regions interspersed with sequential parts, and it can be nested. So I can have a thread cruising along that goes, hey, I could use a couple more threads, man. It could fork them off right there. So you can have nested parallel regions. Okay, that's the essence of programming with OpenMP, programming with p-threads, programming with Windows threads. This is the essence of multi-threaded programming. So the way we create threads in OpenMP is with the parallel construct, pound pragma OMP parallel. And we use the word region. I'm really a stickler for using the right words because that helps understanding. We use the word region to refer to all of the code accessed inside the construct. Okay, so I'll get these words in a moment. You create threads with a parallel construct. So we have an example here where I create an array A of the length 1,000, and then OMP set num threads is a call to the OpenMP library, and I'm requesting 4 threads. So OMP set num threads 4 is a library routine provided as part of OpenMP, and I'm requesting 4 threads. So now I do the fork, pound pragma OMP parallel. Now we have a bracket and then a closed bracket, and in between those brackets, I have 2 statements. Now that defines the construct, the directive plus the code between those brackets, we call a construct. All of the code called, like the code inside that function poo, we call the region. So I'm going to get these definitions out of the way at the beginning. Now notice inside the construct, I have int ID. So I'm declaring a variable inside the construct, and I'm setting it OMP get thread num. OMP get thread num will return an ID, a rank between 0 and the number of threads you actually got. So in this case, assuming I got 4, 0 to 3. So all of the threads will redundantly execute that code within the construct. It's pretty straightforward. Okay, so we defined the parallel construct, pragma OMP parallel. We've defined a runtime function to request a number of threads, and a runtime function to get the ID. Just to belabor the obvious, because the details are very important, let's walk through what happens at execution. So, and I have a little box there that shows the code. We wrote this from the previous slide. Here's how it executes. So the initial thread's going to come along. The initial thread's going to create that array. The initial thread's going to do that OMP set num threads. Now I come to the block, and every thread, let's assume I got 4. Every thread's now going to set its ID, and then that thread is going to go with call that function poo. And the first one with ID 0 will go poo 0a. The next one with ID 1 will be poo 1a. So there you go. They're all going to call that function. And then when they're done, they're going to join back together again. So that's how it executes. Now, crudely, and we'll go back and dig into this in much, much, much more detail. But crudely, the way I want you to think about it is if you declare something before the parallel region, so that array A, if you declare something before that parallel region, it will be shared inside the parallel region. If I declare it inside the parallel region, like the integer ID, then each thread will have its own copy. Okay? So we say that it's private to the thread. So every thread on the thread stack will have a variable ID. And every thread will be able to see the same array A. Okay? So that's the big, I'll get to this slide in a second. So I want to take a pause here and deal with questions. So someone asked about, on the hello example, I didn't create threads. And it's like, yes, you did. You had the pound pragma OMP parallel. Pound pragma OMP parallel creates threads. Now, if I don't go OMP set num threads, then I get the default number of threads. So if you don't tell it how many threads to create, it has some idea, it has some default number. And we'll talk about that a lot more later. So if I did just pound pragma OMP parallel, it's going to give me however many threads it feels like, depending on the system defined default. So in this case, I asked for a specific number. Give me 4. But if I left that off, it would give me whatever the default is. And the default is usually the number of cores. So on my laptop, it's a dual core laptop, but because of the symmetric multi-threading, the operating system thinks there's 2 cores per physical core. So my operating system thinks there's four cores. So the default on my laptop is 4. But on Cooley and Theta, these are much beefier chips. You know, your default is probably however many cores, 12, 18, 24, whatever the number is. Okay, so there we go. Any other questions? All right, let's talk about the number of threads. And I am extremely careful in the words I pick. Notice I've always said, OMP set num threads 4, you are requesting 4 threads. Let's be clear, you request a number of threads. The system has the flexibility to come back and say, nah, I'm not going to give you that many threads. Now, this is really important. So imagine on the system you're running on, imagine I didn't have enough nodes for each of you to have your own interactive node, and you had to share nodes. That happens. So you're sharing nodes. My system administrator may decide that I'm not going to let one person hog all the cores. So the administrator setting up the system may say, no, I'm going to let anyone only have no more than 8 cores. So you only can have up to 8 threads. So we had to define the standards so that the system administrators could manage the system to support their needs. So we do not define in the OpenMP standard how many threads you get when you request. It's up to the system. And so it's a little bit irritating because it means that an implementation could silently give you fewer threads than you asked for. I could ask for 4 and it could say, nope, you're only going to get 2. Now let me emphasize, once you are given the threads in a team, it will not be reduced. So you're not going to have a team of 4 threads cranking along, yeah, 4 threads, and then the system says, nah, you only have 3. So once you have once you have a size of threads in a team, you get that through to the end. So what I have here, and I think I got a slide, yes. So I request a number of threads, and then I have a runtime function that tells me how many threads I actually got. Int n threads equals OMP get num threads. So that will tell me at any given point, how many threads do I actually have in the team? And this is how I can figure out how many threads I have in the team. Okay, so there's a couple questions. Why limit the number of threads? We can just schedule them sequentially. We can, and some systems will do that. Okay, remember, a modern operating system, to create the illusion of interactive, low latency interaction, a modern operating system has dozens and dozens, if not hundreds of threads active and able to make forward progress at one time. And it swaps them in and out. So the questioner here is saying, well, gosh, if I asked for 1,000 threads and I only have 4 cores, give me 1,000 threads and let the operating system do its job. And way back in the 90s, we did a system, it was a project I did with Caltech on something called S-threads. We used that for dynamic load balancing, and it worked very well. The problem is the oversubscription problem. When the operating system is swapping threads in and out, you're losing efficiency because you're paying overhead for the thread swap time. But it's even worse than that, because if you swap out a thread and swap in another one and it does an operation, it can change the structure of the cache. So as you're swapping in and out, you can actually create cache inconsistencies between the threads, and that can be a performance glitch. So as a rule of thumb, you don't really want more threads in your OpenMP program than you have virtual cores to run on. So that's why we let the system reduce the number of threads. Okay, so off we go. And there's a question someone raised that, can we move general questioning to Slack, because then it continues after the session. I have both my Slack window and my Zoom chat window open, so I will see you if you put them either place. So to me, it doesn't matter. And there's another question about what would happen if I put the line int ID inside the function poo. I'm going to talk about this later, but I will just briefly mention, when you start a function, when you launch a function, the system will set aside a stack data structure of memory for that function. So any variables declared inside the function go on the function stack. And that's private to the thread. That's private to the function. And therefore it's private to the thread. So no problem if I had the ID inside the function. The thread that calls the function would then be the same thread that called the ID statement inside the function, and it would get the right value. So I'm going to say it again later, but I just want to point out, when things go on the process heap, they're shared. When they go on a function stack, they're private. So for the more subtle cases, this is how you can distinguish between when variables are shared and when they're private. Okay, so, but I need to go on because we're coming up on a real juicy exercise. That'll be fun. So I jokingly refer to this as the Hello World program of parallel computing. I know your MPI, I believe your MPI tutorial yesterday referred to this at one point. We all use this when we teach parallel programming. And we use it because it's easy. It's easy to understand because it's not very likely you get to a course like this without having had a little bit of calculus. It's easy to understand. And if you do it right, you actually see speed up. So we're going to compute the area under the curve. And we're going to do it by filling in a rectangle step by step by step across the curve. So we're replacing that integral with this sum. And then if you're really into integrals and solving integrals on your own, trigonometric substitution and all this fancy stuff, you show that the integral going from 0 to 1 will equal pi. So I have a way of checking if my answer is right, because after doing the sum, I'll get something approximately equal to pi. Okay. So here is the serial pi program. And in the exercise directory, OMP exercises, I give you this code, pi.c. And so you don't have to write this code yourself. I give it to you. All right. And so here's the next exercise. Oh, I'm sorry. Before I get to the exercise. One other function I want to tell you about in OpenMP. So I can, and actually it's inspired by the MPI analog function. That's why I pushed for calling it W time, because it's like, well, MPI has a W time. We should have a W time. So it's wall time. Remember, OpenMP was a couple years after MPI, a few years after MPI. So we all learned from MPI and we created OpenMP. So you can time things by, you call OpenMP get W time, OMP get W time, and then you take the difference between that value and then OMP get W time after, and that gives you a weighted time close. So now we come to the first exercise. And notice what I've done here is I try and save you from having to flip back through the slides to get the spelling of specific constructs, because that's not productive use of your time. So when I give you an exercise, I will put on the assignment slide for the exercise all the constructs that you could need. Oh, I've got a typo here. Oh my God. There is not a punctuation mark period after the pregnant. It's pound pregnant OMP parallel, not pound pregnant OMP parallel period. So at any rate, what I'd like you to do is take that pi program, put in those, make sure you can run it, then put in those timing calls, and you have to put in the OpenMP, pound include openmp.h. And then what I want you to do is just using what's on this slide. Those of you knowing some OpenMP, don't cheat. Just using what's on this slide. Pound pregnant OMP parallel, OMP get num threads, OMP get thread num, OMP get W time, OMP set num threads. That's all you're allowed to use. Create a parallel version of that pi program. And this one can take a while. 50, if you're really, really good and have some experience in parallel computing, this will take you 15 minutes. If you're hopelessly stuck, this could take up to half an hour. But I really want you to take the time to get this one right. Now, someone pointed out in the Zoom chat an excellent point, and I agree with them, that if we move our chat conversations to Slack, then it's there after the Zoom session goes away. So what I'd like us to do is, you know, for telling me you're done, something ephemeral, you know, like that doesn't matter, go ahead and use the Zoom chat. But for any questions of real substance, let's deal with them through the Slack channel so that they continue after the session's over. All right, go for it.